Okay, in this video, we're going to go through a couple more theorems, and then I'm going to show you how to apply those theorems in a couple more examples. Okay, so the fundamental theorem of algebra says every polynomial that is degree 1 or higher has at least one complex zero. And for a quick refresher, a complex number is written in this form, where it's a plus bi. A is called the real part, and b is called the imaginary part. So if you had a solution or a zero that was a real number, that's actually considered a complex number too, because we would just say the b is 0, that there is no imaginary part. So for example, just the number 3 can be written as 3 plus 0i. So all reals are complex numbers, but not all complex numbers are real numbers. If there's an imaginary part in there, a b that's other than 0, then it's going to be considered an imaginary number, versus if b is 0 and there is no imaginary part, then that falls into the real category. Okay, so the linear factorization theorem, we kind of already hinted at this already, but now we can formally write it down. Okay, every polynomial of degree n has n linear factors when we write it in factored form, and therefore has n number of zeros. So that means if you have a degree 4, then you're going to have 4 factors when you factor it out. And for each of those factors, you're going to have a 0, because you'll set each of those factors to 0 and solve for x. Now, some of them might be repeats if you have a multiplicity of 2 or 3. But if you include those multiplicities as separate zeros, then you're going to have the same number of zeros as the degree of your polynomial. So if you have a degree 5, you should have 5 zeros. One of them might have multiplicity of 2, so you count it twice, but when you add them all up, you should have 5. And that's what the linear factorization theorem is saying. Okay, one last theorem, and then we're going to go and do a couple more examples. If a polynomial has real coefficients, meaning your coefficients in front of your x's don't have imaginary numbers in them. They're all real numbers, things that come off the real number line. And the polynomial has a complex 0, a plus bi, where b isn't equal to 0. You have an imaginary part in there. Then the polynomial must have, and I want to underline must have, another 0, a minus bi. So in other words, if you have a 0 that is imaginary, that has the imaginary part to it, then they have to come in pairs. So if I have, say, 4, let me write this down, 4 plus 3i as a 0, then 4 minus 3i has to also be a 0. Okay, and these are called conjugates. when you just switch that number, the sign of that number that's in front of the imaginary part, you just switch that number and that would make it a conjugate. Okay, so now we're going to use that complex conjugate theorem to do the next couple of examples. So we're going to find a polynomial that's fourth degree, meaning by the time we're done writing it out, we should have 4 factors. Okay, so we have a fourth degree polynomial function that has -2, 2, and I as zeros. I'm going to have a leading coefficient. I don't know what that is yet, so I'm going to just write in A. Now, if -2 is a 0, then I should have a factor of x plus 2. If 2 is a 0, then I should have a factor of x minus 2. If I is a 0, then I should have a factor x minus I. But we're not done yet because look, it's a fourth degree polynomial and we only have 3 factors. So this is going back to the linear factorization theorem. If I have fourth degree polynomial, I should have 4 linear factors. I only have 3 as of yet, but that is because we're missing a factor. If we go back up and we look at our conjugate theorem, if we have a complex or an imaginary 0, it has to come in pairs. We got to flip the sign of that imaginary part, and that's also going to be a 0. So I also have the 0, -I. These have to come in pairs. So that means I should also have a factor of x plus I. So now I got all 4 factors. So I'm going to use the extra point that's given to me to plug in for x and y so I can find my value of A, my leading coefficient. So I'm going to plug in -150 for y, and I'm going to plug in 3 for my x's. Okay, so I get -150 is equal to A times 3 plus 2 is 5. 3 minus 2 is 1. Now I have 3 minus I and 3 plus I. And I can do this by hand by writing out 3 times 3 is 9. And then 3 times I is 3I. And go through and actually FOIL it and use the rules for imaginary numbers to simplify it. However, to make things easier, if you don't want to do that by hand, there is an I button on your calculator. If you look at your calculator, right above the decimal button at the bottom, above the decimal button, and mine's in blue, yours might be in a different color depending on what model calculator you have, but mine's in blue, it has a little italics I. That's your imaginary I. So you can actually plug in on the calculator and put in parentheses 3 minus I using that button, so you'd have to hit the second button first to access it, close parentheses, then open parentheses 3 plus I, close parentheses, and when you put that on the calculator, it will multiply that for you with the I's in there. And when you do that, you get that 3 minus I times 3 plus I is actually just equal to 10. So I have A times 5 times 10, which gives me a 50A, which means A is going to be -3. So my final answer is going to be -3, and then I have x plus 2, x minus 2, x minus I, and x plus I. Now, I personally do not care if you leave it like this, but I'm pretty sure, don't quote me on this, but I'm pretty sure that when you do your XYZ homework, it doesn't have an I button in there for you to use on that pad, that template pad. So when you do this part here, you're going to have to write it without an I. So this part you're actually going to have to multiply out. So you would have to rewrite this as x plus 1. So if I take x times x, that gives me x squared. Because it's the difference of squares, the middle term cancels out. And then I get negative I times positive I. That gives me a negative I squared, which is equal to positive 1, which is where we get the x squared plus 1 from. So on x, y, z, if this was a problem, you would actually want to write out your answer as negative 3 times x plus 2 times x minus 2 times x squared plus 1, because it doesn't have the I option on there for you to use. But when you're writing it out by hand on a quiz or exam, you can leave it just as is, and I'm totally fine with that.